The objective of this, my second video, powering up my 1800 watt ZVS induction heater, is to show people who are newly involved with this 1800 watt model how I have hooked mine up and how they might hook theirs up without creating problems for themselves in the future, and a little bit about showing you what you can expect from this system. This is the current setup. I'm running the fans and the little water pump from a small 12-volt battery because I am not yet using the buck converter that came with the system. I got some early on info that some of the buck converters couldn't handle the 48-volt input power, and I think this one would, but anyway, I'm just powering it up. Separately, this is just a plug and jack for powering the thing up. There, and with a little LED on it so I know it's going. This is my current radiator. I recently added a fan to the system, which I'll power up in a minute. I've got a Celsius reading thermometer here measuring the water temperature. Starting at the power supply, this is an Emerson something 2900 server hot swap module power supply, 48 volts. I think it's I don't know, it says 40 amps or something like that. But at any rate, these are the DC outputs here. Somebody had marked a little plus mark on the bottom one for me. I verified that and made it red to help me remember. The thing came with a 2-conductor 120 volt cord with the standard 2-prong parallel prong plug for the USA. But I found that the power supply won't deliver full power on 120 volts, so I stepped it up to 240, and so both lines are hot, and I added a ground wire. There's a pin sticking out right above the little connector here where I could plug in that ground lead, and so made myself a 3-conductor plug and a 250 volt receptacle right over there that I'll plug that into later. I have a multimeter here that is connected to the power supply, so I can just see whether it's sagging or not as I add power. And in the output circuit, I'm using 10 gauge wire, by the way. I have a automotive type amp meter here just as a rough check of the current flow. That's in series with a 75 millivolt shunt that goes to this amp meter right here, which again has a 0 to 50 amp scale so that I can watch changes as they happen, not having to wait for the refresh rate on an LCD type meter. I have a small oscilloscope here that I had been using to measure the gate signals. I won't be using that today. I just recently added this 120 volt fan to my radiator, and I know that's not all that efficient. Later on, when I upgrade this whole thing from a breadboard into something that's more compact, I'll add a plenum to improve the efficiency of cooling. But for today, it'll be good enough to just see how much heat that can take out of the water. Okay, we'll power the thing up here, and you notice it'll take 4 seconds before we hear the power supply start to make noise. So, you know, it's a switch mode power supply. It knows enough not to put anything on the output lines until it's up to voltage. And then the last thing we have to do to prepare for operation is to turn on the radiator cooling fan, and I'll do that here. And you can see that it's a pretty loud fan. Then to actually get something going, we'll throw the circuit breaker and today we're running at about 4 or 5 amperes idle current, which is normal operation for this system. We see the power supply is putting out 48 volts. Again, for reference sake, the temperature is 16.6 degrees. And we're off and running for the rest of the video. I will be putting the camera on a tripod, so you may not be able to see the meters, so I'll try to continually call out what's happening so that you're up to speed on what I'm doing at the moment. Okay, here we go again. This time we're going to turn a timer on so we can keep track of how much time we've got into this whole test here. And water temperature is 17.3 degrees, 48 volts into the out of the power supply, 4 amps here, verified by that meter there. Again, the power's on and so on. So I'm going to now put the camera on a tripod, and we're going to focus on the work coil, and I'll just try to remember to shout out the numbers as they happen. Again, the 4 or 5 amps idle current, 48 volts, 17.8 degrees Celsius on the water. We're 2 minutes into the test because it took me a little while to put the camera on the tripod, and away we go. I want to make a note that the diameter of the coil here is quite large compared to the 1000 watt model. I think they do this to keep the coil farther away from the work that you might stick in there, which means you're less likely to go over current by putting something too big in there. But that's just my opinion. So some of the other things we'll do later on is to try adding a few turns and reducing a few turns on the coil and maybe making it a little bit smaller. I don't see much need to make it bigger in diameter anyway and see what happens, but that's for another day. Again, water temperature 17.9, and that's nice because that means that our 4 amps is hardly doing anything to the work coil. I mean, it's still, the pipes are cold to the touch. Whereas in my previous video where we were running 14 amps, there was a lot of heat generated, and that water was heating up. That 2 quarts or so of water that's in the radiator was heating up pretty fast. We're now going to insert a few things in the work coil and heat them up for a few seconds just to see what happens current-wise. At this point, we're not going to make a big deal about making things really hot. Maybe we'll do that toward the end of this test. Let's try a 1/2 inch square bar. Again, 4 amps. Goes up to 19 amps. So that's 15 amps times roughly 50 volts. So that's about 750 watts going into the coil. I put that in at about 4 minutes and 15 seconds. What did I say it was? Anyway, it's now gone up to 22 amps, which is kind of a surprising thing that happens with steel. We haven't got to the Curie point yet, but for the first little bit, when we put something in, the voltage or the current does seem to climb during that first part of the heating process. We have pretty good light on here today, so we're not going to see things glow until they get pretty darn hot. I can now see a little bit of a glow. I don't know if you can there. So back in there, still 22 amps. We're at 511. So that's about a minute to get it to glow at one point. Okay, but the big point is that we're looking at the current. Current's already starting to drop pretty good. Now it's back to 18 amps. 17 amps and so on as parts of the steel, mild steel, get up to the Curie point. Okay, now we're going to stick the end of this 1 inch square bar in there and see if we can drop it all the way down to the bottom. 25, 30, 35 amps, 35 amps. Temperature of the water 18.2. Time into the test that I had it on, 8 minutes and 20 seconds. 37 amps. 37 amps. And we don't need to heat stuff up really hot right now, but the point is that that a 1-inch square bar and this 2 3/8 ID coil is getting me up to, now it's 38 amps. So that's a lot more current than I was able to try to push for with the 1000-watt model. And things seem to be okay. So I don't have to go any further than that. We know what's going to happen when we get to the Curie point. I don't know how long it would take. That's another test. Okay, enough of that one. Find a place to put him where I don't burn something else. Current's back to 4.5, 5 amps. Water temperature 18 degrees. Boy, that feels that way too. That's great. I'm going to test the MOSFETs just with my fingers. They all feel very close to the same temperature. One thing that I want to comment about that I didn't say in the last test is I have now insulated everything with a thin piece of plywood on the whole bench here so that I don't short anything out. And I've also raised the board up on another couple of inches, 1.5 inches of material. When I was having trouble with the too high idling current, I thought maybe there was some kind of inductive thing happening when the board was only 1/4 of an inch above the metal shelf that I'm sitting things on. So I raised that way up and it didn't make any difference at all. So that wasn't part of the overcurrent issue, which I still don't know exactly why it happened. My best guess to this point is there might be a crack in the board someplace that I twisted one way or another when I was messing around resoldering joints and so on. Still don't know really. Okay, quickly, MOSFETs, 76 degrees Fahrenheit, 80 degrees Fahrenheit, 70 degrees Fahrenheit, 70 degrees Fahrenheit. I think I found before that one that over in this far corner seemed to be running a little hotter. And I did say, and I'll say it again, that I think the specs are different. The actual on resistance varies a little bit from board to board. May also be due to slight differences in the drive circuit. Okay, moving on. Now I'm going to put the insulated crucible in here. And I've got this pair of, I don't know what you call them, some kind of cook's tongs that I bent up so I could hold this crucible and other ones to get it in and out of there. As a backup plan, I've got a big pair of blacksmith tongs that I can use. And another kind that I could use if I had to, anyway. Okay, so here we go. 4 amps, putting the crucible in. 10, 18, 20, 25, 30, 32. And I've got the crucible jacked up just a little bit, so there's probably 3/8 of it that isn't all the way down in the bottom. So right now it's drawing 32 amps. From a test I did yesterday, if I take one of my little support pieces of ceramic out of here, the current would go up to maybe 36 amps. Water temperature staying at 17.9. That's really great. 12 minutes and 48 seconds into the test. Let me just check those MOSFETs again while this thing is in here. .3, 72, 71, 71, 75. That isn't a really big difference, is it? And this thing isn't necessarily all that accurate. This is a little Harbor Freight special. 30, almost 32 amps. That's starting to glow and smoke, I might add, which isn't a huge surprise since it's ceramic, and who knows how well cooked it got. Oh, a little bit of flame. Looks like we're curing our crucible as we go. I don't know if we can see down in there without moving my... Yeah, you can see a little bit of glow in there. So that's coming up to temperature. Now this is graphite, not steel, so we shouldn't see a Curie effect from this guy. So probably just as well to take that guy out of here. Again, this is just to see what happens current-wise. So we'll take him out of here. And I've got a fire brick behind the camera, a big one, so I can set stuff on there to try to keep from burning myself. Now I've got this piece of water pipe, and it's 1 5/8 in diameter. Is that 1 or 1 1/4 pipe? You know, it's water pipe scale. I think it's 1 1/4 inches. So let's just stick that in there and see what we get. This being hollow, you know, this is a 1-turn coil. So let's see what happens. So I'm putting it in there. We've got 5 amps, 10, 20, 25, 30, 35, 45. It would go, by the time I set it all the way down there, that's 45 amps, probably pushing it. Let's just hold it at about 35. So there's only about 2/3 of it in there, and it's galvanized. It's galvanized. So I don't want to really cook it too bad. I don't need zinc fumes in the house here, in the shop, I mean. But boy, that'll go up to 50 amps real quick. Okay, after having done that, we're 16 minutes into the test. Water's at 18 degrees. Boy, am I super pleased with my radiator. Okay, I blew a scene here a little earlier, and so I've got to reshoot the scene where we try and heat up some copper wire with a crucible. So I had to reset my timer. We have everything on and ready to roll here, except we're only 1.5 minutes into me restarting this thing. And so we'll try to heat up this little crucible that's got copper wire in it. The copper wire looks black because I already did heat it up once, enough to oxidize it, and I didn't melt anything quite, but some of the parts did stick together. So this is going to go in there, and we're going to see what happens. So here we go. The water temperature is 16.9 Celsius. The idle current is about 4.5, 5 amps. Power supply is at 48.0 volts. Anyway, there we go. So now we're putting the crucible in, 10 amps, 15 amps, 25, 26 amps. Back down to 20 when I take my metal tongs out. But anyway, so we got 20 amps going in there. And that was what, at about 2 minutes and 40 seconds or so. Well, it's already too hot for my little temperature tester here, which goes up to, I think, 700 degrees. We are just going to see what happens when we heat this thing up. Now, it's important to note that, again, we're reading 20, maybe 21 amps with 4 amps of idle current. So what's that? 17 times 50, whatever that's, I don't know, 800 watt, whatever that is. Okay, things are glowing in there already. I'm going to put a cover on here to try to hold in more heat. There's a little bit of flame in there as the crucible cooks. That could have been bigger, couldn't it? Smoke. The whole test we're 4 minutes and 24 seconds into it. I just bought this insulation recently. I thought it was good for a higher temperature than it appears to be, because as you can see, it's already blackening. 4 minutes and 38 seconds. The water temperature is up to 17.3 Celsius from whatever I said, 16 something. So it's just climbing a little bit. Current is still 21 amps. And of course, we wouldn't expect the current to drop, because this is a non-ferrous crucible with non-ferrous material in it, so we don't have that Curie point thing to bug us. So let's take a peek here, see what's going on. Pretty warm in there. Still 21 amps. And I figure that's about 810, 816 watts of power that's being pumped into the crucible. 534, probably about 3.5 minutes. It's going pretty good in there. This isn't supposed to be a melting demo, really, but I just wanted to see what would happen with that size crucible in this 2 3/8 ID coil. Now, if that crucible was bigger, we'd obviously see more power being transferred, more energy being transferred, like we did when we, or like we will do when we put the bigger crucible in. Oh, I see something moving around in there. We might have some melting. We do. We really do have some melting going on inside there. Great. It just all melted. How about that? We just done melted some copper, folks. I'm just going to turn the power off. Hopefully, and that's at 6.5 minutes, and I think we started heating this at about 2 minutes on the meter there, so it took about 4 minutes to melt that much copper. I'm really unprepared with something to pour it into safely, so I might try pouring it unsafely. Let's see. No, I'm not going to do it. But we have this beautiful little copper thingy here. I'm just going to pour it out onto my, where are we here? There, I'm just going to pour it right out there. I waited too long, it hardened up. Yeah. It's in there, but it hardened up on me. Sorry about that for half of a demonstration, but at any rate, we certainly can melt that much copper in a short period of time, and that's only half the current that this system could produce. MOSFETs, 73, 73, 74, 80, still doing good. This is my little buck converter that I pointed out in the previous video that I wasn't using. I know we're not drawing any power from it, but I just thought I'd leave it plugged in just to see if it burns out on its own or something from the 48 volts. But this happens to be one that's got the LM2596H or HV or something on it that says it's good for 60 volts. And the input capacitor here is a 63 volt capacitor. So, for this particular test, I'd say that's kind of it. We've tested some stuff. You can see how it works. Yesterday, by the time I'd been about 5 minutes into the test, the water had heated up to about 60 degrees Celsius now. And the water had expanded from about down here all the way up into my funnel. So it had gotten a lot hotter. So even though my fan is noisy and I don't have a plenum on it, boy, it just has really got great control of the heat. So I could see this setup, you know, being able to be used for a long period of time. Okay, the last thing we're going to do is, this is a piece of tubing. It's about the size of 3/4 inch water pipe, and I've kind of insulated the inside of the crucible with some I don't know, high temperature insulation of some sort that I bought a little while ago. And see how hot that would get. It's only drawing 14 amps. I would have thought it would have drawn more than that. But that's about 10 amps. That's about 500 watts, right? "27 minutes into the test, 19.1 degrees on the water. 12, 10, went up to the Curie point, dropping down 9 amps. I thought that might get a lot hotter than that, but that's, again, it isn't much amperage, and it's because that pipe is small and the coil diameter is big. I don't know what you're seeing on the video, but I'm seeing just a low red glow just over the Curie point, probably about 1500 degrees Fahrenheit. We're down to 9 amps, maybe 8 if I was looking straight at the meter. So that means we've only got 4 or 5 amps, 250 watts. It helps to insulate things a lot. So, you know, you saw the insulation I got there. Here's a piece to put on the top for something, and all that sort of helps when you're trying to get something really hot. When I was heating the copper, I had forgotten, but I really should have been putting a lid on there, because that copper is radiating, and so is the crucible, radiating a lot of heat up and out. At any rate, I guess that's it for today. So it got hot, but not really. So what are the final numbers here? We went from about 16 degrees Celsius to 19 degrees Celsius. We had excursions from about the 4 or 5 amps of idle current up to, I think at one time, we even momentarily went up to 45. The power supply, and I guess I didn't read the voltage off, I've never seen it go below about 47.8 volts, no matter what I was doing to the rest of the system. Again, the water is just, boy, that's great. This is, you know what, it's, you can still feel it's cold coming in, and it isn't even body temperature going out. Well, there it is, 19 degrees Celsius. So I'd say everything works. Let's give it a MOSFET temperature. Of course, they've had a chance to cool now. 76, 72, 71, 80. That's it for the power on testing part for today. Well, how do I sum up this particular video? I guess I'd say, hey, it works. Hopefully you can see what to expect from the power capability of this system. And of course, this is the 1800 watt model. So I suppose if you've got a big enough power supply, you could expect another, you know, close to a third more output from that 2500 watt unit. I'll just add, but you've got to take this with a grain of salt, that the power supply that I'm using, that Emerson something something model 2900, it actually in the specs it says it's 2900 watts capable. So maybe with that would be able to push the 2500 watt supply as far as you want to go. Obviously a 35 amp breaker such as what came with this isn't going to work for the DC power out. Just want to remind anybody who gets one of these with that power supply is it'll work as low as I think 72 volts AC, but it won't put out many watts. So I think it's still only I don't know, 2/3 the power at 120 volts. So that's why I switched to 240 volts for this power supply. Next, I'll do some more testing, pushing the system for extended periods as I have done with the 1000 watt unit. Then I need to make this system more compact so I can move it around. My last comments are, please feel free to make any kind of comments about what you have seen. And also, I encourage you to ask any questions that come to your mind. I'll do my very best to answer them. And if you do feedback to me, it can only help make me a little bit smarter, because I'll probably have to dig deeper myself to give you the answers. So thank you for watching.